So it's time to run our first container. In this case, a container with shell access. The kubectl run command is pretty similar to the Docker run command. The syntax is a bit different, but it basically does a similar job. So in this lesson, we are going to look into container shell access, which basically is starting at an interactive container, as we did with Docker. And the reason why we're doing that is because sometimes using kubectl proxy alone isn't enough. You want to issue some commands to discover the environment because you have made assumptions and they obviously don't work because your deployment failed. So you want to get a feeling on where your assumptions might be broken. So having an interactive container can be very handy, especially during debugging. For example, you can start a container and use a curl command to issue a HTTP request against other Kubernetes applications running in the cluster from within the cluster. Well, you can do that with curl and using the proxy, but sometimes you need, for example, more of the Kubernetes environment that is given by the kubectl proxy. For example, you could start a container and mount a secret or a config map into that container and then try it out, how it feels to be in that container, what are the environments variables look like, and so on. So this is a tool that you should know. That's why we starting container with such an interactive shell. All right. So we are basically in a container now. So there's been a container started in our cluster. But the container is within a pod. This is a very important point to make. In Kubernetes, you cannot start a container directly, but you start a pod. A pod, it can have one container or it can have several containers. In this case, it has only one container, but it is a pod nonetheless. So the idea of a pod compared to a container is a pod is a collection of containers. This collection of containers will always be scheduled on the same Kubernetes node. This means that it won't happen that container 1 is on one node and container B is on another node, which means they couldn't really interact other than using Kubernetes services or referring to each other by network connections. Within a pod, there's always a loopback device. So if you're familiar with loopback devices, it's quite common that you have a network interface, where is it here, that has the IP address 127.0.0.1. And this loopback interface is basically like a dummy network interface that is allowing or restricts network traffic to your local computer. So for example, you can ping your own computer. If you remember that session from last time, we've run into an issue where we bound a web server process within a container to the loopback device, and then we haven't been able to connect to the web application running inside the container, although we have created a proper port mapping. And the reason for that was that the loopback device usually does not allow network traffic to other computers. But in the case of a pod, the network device is shared across the containers of the pod. So whenever you bind a service to the loopback device and open a pod, other containers of the same pod can talk to that particular container. So as if you were running these processes from within a single container. So the pod allows you to structure a system that would usually run as several processes into several containers, while keeping those containers very close together. Very close means they will always be scheduled on the same node, and they can talk to each other through the Loopback device, and they can also have volume mounts. For example, they can mount the same config maps. They can also talk to the same persistent volumes that they can mount into the file system. They can also share non-persistent volumes. So there will be, I think, beside of direct process communication, not sure about that, but beside of that, there's plenty of ways how containers in a pod can collaborate in a way that, for example, pods cannot communicate with each other. All right. So you can see that we've created the container, and we also like to see kubectl get pods. There is our container within the pod called BusyBox. All right. So we can, as we can see, there's a file system. In this case, the container, once it is stopped, is terminated. So in contrast to what we've seen in Docker, where you can restart a stopped container, in Kubernetes you can't. As far as I know, you can't. And the reason for this is it really doesn't make so much sense in Kubernetes to restart a container, because when you restart a container, a container has failed or a container has been stopped, it will be rescheduled. It will be recreated, so to say. A new container will be recreated from the same image, but the container image won't be restarted. All right. You can also see that within such a pod, there's a list of environment variables that allow you to, discover the surrounding Kubernetes cluster. For example, you can see a few information, like there's a host name, there are Kubernetes IP addresses set, so that you can also reach out to the Kubernetes API from within a pod, and that you know where to connect to, because these things could be configured differently in different clusters. But more to that later. All right, so we've created that interactive pod. And when we stop that process, the container will terminate. So the pod is considered completed. And if you look into the kubectl command, there's no such a command as to restart a stopped pod, but you have to create one. So if you remember that experiment we did in Docker, where we started the Docker container and we then wanted to execute a command inside of the running container, and we've used Docker exec for that. So Docker run to run and start a new container, and Docker exec to run a command within a running container. So let's try whether we can do that in Kubernetes too. All right, so we try to rerun the container in the sense that we create another container, and you can see that the BusyBox name is already taken. This is also similar to Docker. because while the pod is completed, it's still there. And there's a reason for that. For example, if you want to get the logs of the pod, you could kubectl logs busybox. So there's not much of the logs here beside of the output to standard out that we have created with our commands. But as you can see, the pod is still there, and you can still inspect the pod using the command. So you could also, I'm not sure whether you can describe the pod, busybox. Yeah, so there's still a track record of the pod. For example, the pod had the internal IP address from within the Kubernetes IP address pool 172.70.05. You can also see metadata such as labels, so you can label and annotate entities with key value pairs, start time, priority. You can also see that somehow our setting of the namespace didn't work. I will figure out later why this didn't work and fix it. You can also see that the state of the container is terminated and that it has been completed, which meant that there was no failure, for example, because containers can also terminate due to failures. So there's a lot of information to dissect. And in particular, the one that could be interesting for you when looking into problems is the events section. Because containers may fail for several reasons. For example, there could be something wrong in your container description. For example, there could be an application error so that a process terminates, which will then in turn cause the pod to terminate. Or, for example, there could be something wrong on the level of the Kubernetes cluster. For example, there could be enough resources, or the container image cannot be pulled, which can go back to a false specification by referring to a container image that doesn't exist. So this is where you could, get information about that. So in particular, yes, this is where the image has been pulled, and if the image can't be pulled, you will see a notification here. Also be aware that if the container image can be pulled, the container couldn't be started and there wouldn't be logs. So a command for a container that has failed wouldn't produce output. On this one, you'd get an error message. All right. So what do we have to do? We have to delete the pod. This is pretty similar to what we've done in Kubernetes. Once we've deleted, we can create a pod of the same name. All right, so the pod is running. We can confirm that. Get pods. Pod is running. And now we create another shell. Before we do that, we use this shell and create a process that will be there for a while, so we can see whether this is really the same pod. And as you can see, here's our sleep, which means that this is not a fresh pod, because then the sleep command wouldn't be there, but it is the pod that we have created in this tab of the terminal. All right. And we clean up, delete the busybox. So, as we have learned in this little section here, it is possible to create an interactive container similar to what we have done with Docker, which gives you the ability to interactively explore the environment. Imagine you have created your own image, you want to create your own pod specification, but something doesn't work. So you could try to modify the pod specification so that you can start an interactive pod and see how the actual environment looks like, to figure out how, for example, the start command should look like, or things like that. So because especially if your container images and the code within the container images make assumptions about the Kubernetes environment, this will be different from Docker images that are meant to run inside Docker environments. So this is very important for you to get. We are using Docker images here. So you can create the Docker image with the tools we've seen earlier in the first section of the training, and we can use them in a Kubernetes environment. But obviously, if, for example, you're reading environment variables as the ones we've seen in the earlier example, then this only works if you are within a Kubernetes environment, and this will be the case for config maps and secrets, for example. While Docker and other container orchestrators may have similar features, this will be Kubernetes specific, which usually doesn't really make a lot of difference for base images that restrict to offering a particular service that is usually not making assumptions about the environment too much. But if you're creating workloads for Kubernetes, it is very likely that your container images will be Kubernetes specific. In this case, you will build the container image using Docker, but you will test them with Kubernetes. All right. So we've looked into the container shell access, where we've created our first container in Kubernetes. We have seen the similarities between Docker and Kubernetes, but we've also seen that in Kubernetes it is not possible to restart a container. We have seen that it is possible to have an interactive container, which is handy because especially during debugging purposes.